right? Okay, thank you. Welcome local attendants and in particular remote attendants to the second session of this meeting. My name is Dan Frankel. I will chair this meeting. You probably will see very little of me, but I will try to make sure that the speakers will leave some time for discussion at the end, and the idea is about 8 minutes. I think it's probably best to go ahead right away because at the end there will be a postal session and we don't want to eat into the time of the postal session anymore. So the first speaker in this session is a remote speaker, it's Marjolein Dijkstra from Utrecht, and she'll be talking about machine learning and inverse design of soft matter material. And I have to see when Marjolein appears on the screen. Yes. Okay, go ahead, Marjolein.
Thank you very much for the nice introduction. First of all, I would like to thank the organizers for inviting me and for giving me the opportunity to present work that we did at Utrecht University. And I noticed that the title of the symposium changed from future to new directions in soft matter. So I hope my talk will still fit in the theme of this symposium. So what I would like to do today is to discuss how one can use machine learning and inverse design methods to better understand the self-assembly of colloidal particles and nanoparticles. And over the past 2 decades, due to many advances in the chemical synthesis of colloidal particles, one has now the availability of a vast array of colloidal building blocks that can vary in shape, in size. They can be made of different materials. The interactions are tunable. And so the idea is now to exploit this huge variety of colloidal building blocks and to self-assemble them into new functional materials with novel photonic, plasmonic, and optical properties. And so if we go back to the simplest years, we already know from computer simulation in 1957 that such a system shows a spontaneous crystallization from a fluid phase towards a phase of the cubic crystal phase. And this was indeed verified also by colloidal experiments that were done by Josie and Van Meeken in 1986. Another question that one can ask is, how does such a crystal form out of a supersaturated fluid phase? And this brings me back to the process of nucleation. If you start with a supersaturated fluid phase, then small nuclei can appear of the stable phase. They appear, but also disappear until a nucleus is so big that it exceeds the critical size, and then it keeps on growing until it spans the whole system. And in these pictures, I already show you the fluid particles 10 times smaller, and I denote them in blue. And so if you want to study nucleation in such a system, either by experiments or by nucleation, it would be very nice to have an algorithm or an order parameter that can identify on a local particle level in what environment such a particle is. And for that, we use often the Sinard-Nelson congestion bond order parameters. You first identify the local environment of a particle. You identify all the neighbors of, for instance, the neighbors of this green particle here in the middle. And that can be done, for instance, by a simple distance criterion or a Voronoi construction or more involved algorithms. And for all these neighbors, you then use the spherical harmonics, you calculate the YLMs for those particles, and you can sum over all the neighbors and get these QLM values. You can average over the next nearest shell, and you can make rotational invariance by just squaring these QLMs or using a cubic rotational invariant of that. And often the Q6 and the Q4 bond order parameters are often used to study crystallization because of the 6-fold and 4-fold symmetry in crystals. If you plot, for instance, the distribution functions of the Q6 values for typical fluid configuration, BCC, body-centered cubic configuration, and face-centered cubic crystal configuration, then we see that the Q6 value is relatively low in the fluid phase and it is high in the FCC phase. And naively, one would be able to to conclude from this path here that the fluid always nucleates via the BCC phase. If you just use this very simple projection here, one can try to be smart and use both the Q6 and the Q4 value and make a scatter plot of the typical liquid configuration, hexagonal closed packed configuration, the FCC and the BCC configuration. And if you then plot on top of that a simulation trajectory at different times, as shown here, one may conclude that the fluid already shows HCP-like order and that the nucleation of hard spheres always proceeds via the HCP phase. And this is actually the danger of using all these projections. So one can use a projection only on the Q6 or only on the Q4 and Q6 values. And this is actually what we already know from football or soccer, that if you want to judge whether it's offside or not, it really depends on the projection. So what we decided to do is just not only take Q4 and Q6, but we use the full expansion of the spherical harmonics. We use Q1 all the way up to Q12 or Q24. And we make a very big factor of this for every particle. So we do simulations, we generate configurations. For every particle I in the every configuration, we calculate this factor. And then we use a principal component analysis that is basically a linear transformation of the basis to find the relevant order parameters. And these principal components, or this new basis set, is constructed in such a way that the first principal component accounts for the largest variance in this basis set in the data set, and the second largest. And so if we then do that for typical fluid, HCP, FCC, and BCC configuration, we find that these clouds are very nicely separated from each other. And so if we then plot, for instance, a simulation trajectory, we find that if we start in a fluid phase, it goes towards the FCC and the HCP phase. There are stacking folds in the crystal nucleus, and that's why there are these three lobes here. But what we do see is that it completely avoids the BCC phase. We can do the same for experimental data. This is data from the group of Alfons van Bladeren. They use a very nice trick in which they arrest the system by polymerizing the solvent, and then they can just do that at different times in a nucleation trajectory and then track all the particle coordinates. And so they can do that, they can start in the fluid phase. And if you do the same analysis, what we did for the simulation trajectory, you can see that it nicely goes to the FCC phase. So the next question that one can ask is, how does a binary crystal nucleate? And there's one very exotic, bizarre binary crystal phase, which is the so-called AB13 crystal phase. So this is a crystal phase that is a stable four hard sphere mixture, big spheres and small spheres. There are no energetic interactions between the spheres. It's only excluded form, so the particles cannot sit on top of each other. And this very exotic lattice consists of a simple cubic lattice of large spheres, which are already peculiar for hard spheres because they usually form hexagonal lattice. And this simple cubic lattice has a very large lattice spacing in such a way that an icosahedral cluster of 13 small spheres fits in the center of this simple cubic unit cell. And then moreover, the icosahedral clusters are rotated by 90 degrees with respect to the neighboring clusters. So the unit cell consists of 8 of these icosahedral clusters with all the big spheres surrounding it. And this lattice has been found in PMMA spheres by Pusey in 2005, but they are also encountered for nanoparticle systems. So if you look at the structure of the fluid in the AB13 crystal phase, then one can notice that the structure of the small spheres is very similar in the fluid phase as in the AB13 phase. So this really makes it very difficult to identify the fluid phase from the AB13 crystal phase and to study nucleation in the system. Moreover, the large spheres are really pushed apart from each other in the AB13 crystal phase, and so that makes it difficult to identify the neighbors of the large spheres by just using a simple distance criterion. And so that's indeed what you also find if you use the bond order parameters. Here we use the average bond order parameter, and we see that all these clouds are just sitting on top of each other, which makes the identification of the AB13 phase from the fluid phase very, very difficult. And so that's why we decided to use a neural network. Can we solve this issue by using a neural network? We feed in as an input many different bond order parameters. We use L1 all the way up to 12. We also use the cubic rotation invariant, and we also separate them for every species. We use 2 hidden layers, 72 nodes, and then 4 output nodes that tells us what the probability is that it belongs to one of the large particles in the AB13 crystal phase, one of the small particles in the AB13 crystal phase, or the fluid phase, or the FCC phase. And by training such a neural network with many labeled data, so we use bulk configuration of all these 3 different phases, the AB13 fluid and the FCC phase, we find that the trained neural network has an accuracy of 98 up to 100%. And so this allows us, using the seeding approach that was introduced by Eduardo Sanz and Chantal Valeriani, to study nucleation of this AB13 crystal. So we start with a seed of this AB13 crystal. We put it in a supersaturated fluid mixture. We do Monte Carlo simulations where we fix the pressure. If the pressure is too high, most of the trajectories will correspond to a growing nucleus. If the pressure is too low, most of the trajectories will result in a melting crystal. And right at the critical pressure, half of the trajectories will grow and half of the trajectories will melt. And by calculating this critical pressure, we can also calculate the supersaturation, and using then classical nucleation theory, you can determine the nucleation barrier heights. And that's denoted here by these blue symbols here, and we compare it with just the hard sphere nucleation with also another binary crystal phase. So using this data, we can also extrapolate the barrier height towards higher and higher supersaturation, and we can pinpoint where the nucleation barrier is sufficiently low that we should be able to find spontaneous nucleation. So when the barrier height is less than 10 kBt, we can expect to find spontaneous nucleation. And so that's where we run the simulation, and we indeed find the spontaneous nucleation of this AB13 crystal phase. So we can analyze the trajectory by using a cluster criterion, and we find that the birth of such a nucleus starts with an icosahedral cluster of 13 small spheres, then big spheres are attached to it, other icosahedral clusters are attached to it, and other big spheres. And if you plot just the number of big spheres that attach to the cluster and icosahedral clusters that attach to the cluster, we see really a co-assembly of large spheres and icosahedral clusters. That is very well described by classical nucleation theory. So this is, we can use machine learning to find what the relevant order parameters. We can train a neural network to study the nucleation of several systems, but we can also use machine learning to coarse grain systems. And so often in colloidal suspension, you add non-adsorbent polymer or you add salts to the suspension in order to tune the effective interactions. And so we went back to the good old colloid polymer mixture, where by just adding a non-adsorbent polymer, you can induce a depletion interactions between the colloidal particles. And this whole idea was inspired by the Bailey and the Parinello group. They did electronic structure calculation. They calculated the energy of every atom as a function of the order atom coordinates, and they used radial symmetry functions and angular symmetry functions to basically fit their energies. So these are basically the fitting functions that they use to fit the energy as a function of all the atom coordinates. And so if you have a colloidal suspensions, and I treat the colloidal particles here as hard spheres. You can add non-adsorbent polymers, and that induces basically effective interactions between the colloidal particles due to an unbalanced osmotic pressure, where the polymers can only push from the outside onto the surface of these colloidal particles when the colloidal particles are so close to each other that none of the colloidal polymer coils can fit in between the colloids. And so the simplest model that captures this depletion effect was introduced by Alfines Frey in 1976. He treated the colloidal particles as just hard spheres. The colloid polymers are also treated as a hard sphere-like potential, but the polymer interactions are treated as ideal particles because the polymers can interpenetrate each other. And so for this very simple system, one can write down the total Hamiltonian. This consists of a colloid interaction term, a colloid polymer, and a polymer-polymer interaction term. These are just a sum of all the pair interactions. And if you want to integrate out the interaction, the degrees of freedom of the polymers, it is convenient to treat the species that you would like to integrate out canonically and the other species canonically. So it's a sum of all the number of polymer coils, a trace of the coordinates of the colloids, a trace of the coordinates of the polymers, and then weighted with the Boltzmann weight corresponding to this total Hamiltonian. And so one can trace out or integrate out the polymers' degrees of freedom in such a way that you arrive at an effective Hamiltonian. And so this effective Hamiltonian is this bare Hamiltonian of the colloids plus this omega, which is corresponding to this yellow beast here. And this omega is actually nothing else than the grand potential, the free energy of the C of polymer in the external field of a fixed configuration of NC colloids at fixed coordinates. And this grand potential for this very simple system can also be seen as the minus the fugacity of the polymer times the free volume, and the free volume is just the available volume for the ideal polymer. And the available volume can be split into a zero-body term, a one-body term, a two-body term, and a three-body term. The zero-body term is just the volume that is available for the polymers when there are no colloids present. The one-body term is just the volume that is excluded by each colloid. And then you overestimate it, and that is corrected by the two-body term. The zero, the one, and the two-body terms are known analytically. The three and higher body terms are these very irregular overlaps of all these depletion zones, and they can only be calculated numerically. So that's what we do. All these three body and higher body terms, we just calculate numerically using a numerical grid. We do that for many different colloid configurations at many different colloid packing fractions at a zero fugacity of the polymers, and then we fit it with these Bailey-Parinello symmetry functions. And so if we compare then the three and higher body interactions, these are denoted by these blue symbols, and compare that with the machine learning fit, we find excellent agreement between the machine learning fit and the numerical evaluation of these many body potentials. So here we fit all these colloid packing fractions at the same time with the same machine learning fit. And so we can assume that this machine learning fit is state independent, and it's moreover speeds up the calculations with 2 or more 4 orders of magnitude compared to the numerical evaluation. That these machine learning fits can be assumed to be state independent is very nice, because you can now do also direct coexistence simulations in such a way that you can study the phase behavior of phase coexistence of a colloidal gas phase in coexistence with a very dense colloidal liquid phase in a single simulation box. And so that's what we have done here. The blue symbols are the one with the machine learning fit, and the black symbols are earlier data using either the true binary mixture or an effective one-component system where we use this numerical evaluation of the higher body potential. And also here we find excellent agreement between the machine learning fit and then the previous data. We can also look at structure, pair correlation function, and also there we find very, very good agreement between the two sets of data. So we are now extending this towards charged colloids, anisotropic colloids, but also ligand stabilized nanoparticles where we can integrate out the degrees of freedom of the ligands on the nanoparticles. So finally, I would like to move to the last topic of today. I've already shown you that one can make a zillion of colloidal particles nowadays, and so it would also be nice to have an inverse design method. So the standard approach in either experiments or in simulation is that you start with a certain colloidal building block with a certain shape or interaction potential. You then determine the structure. From the structure, you can derive the properties. But it would be very nice because these the shape and interactions and thermodynamic state points are limitless quantities to turn this logic around. So can we start with a certain property that we are after, derive which structure gives rise to this property, and then find the underlying homotony that gives rise to the structure at a certain state point. And so can we inverse design a certain target structure? So that's the question that we would like to address here. So an inverse design method consists basically out of three ingredients. We first need to model with three design parameters that we can optimize. We then need a scheme to update the design parameters, and then we need an order parameter that is able to distinguish the target phase from all the competing phases and can be used as a fitness function for the design, the update scheme. So the model that we use is a model that gives rise to quasi-crystals. Quasi-crystals is also regarded as nature's impossible phase. It lacks translational symmetry. There's no repeating units. So if you, it's not like a crystal where if you know the unit cell, you know exactly where all the other particles are. In the case of the quasi-crystal, it is not known where the atoms or where the particles are. It does, if you look at the diffraction patterns of quasi-crystal, it shows very sharp crack repeats with a rotational symmetry that is actually forbidden from a crystallographic point of view. So this is a nice challenge to be able to inverse design a quasi-crystal where you do not know where the particles are. So for that, we use a very simple model of ligand stabilized nanoparticles. It is a hardcore square shoulder potential. The nanoparticle is mimicked by just a hard sphere with a diameter sigma, and then the ligand layer is just mimicked by a square shoulder potential with a shoulder width of delta, and then the design parameters are the delta, the temperature, or the pressure, or the density. And so because there are two competing length scales, it gives rise to quasi-crystalline order. So the phase diagrams were already reported for this system. This is the phase diagram for a shoulder width of 1.4 sigma. In the temperature density plane, there's a low density hexagonal phase, a high density hexagonal phase, a square phase, and a fluid phase. And in a very, very tiny density regime, there's a dodecagonal quasi-crystal. And so it would be extremely cool if we can really inverse design and probe this very narrow density regime where this quasi-crystal is stable. So we can also change the shoulder width. We can also stabilize an 18-fold and a 10-fold quasi-crystal, but all of them are stable in a very, very tiny region in the phase diagram. So as an update scheme for the design parameters, we use an evolutionary strategy. We use basically a multivariate Gaussian distribution. The dimension of this Gaussian distribution is just determined by the number of parameters that we want to. If you want to tune, for instance, the temperature and the pressure, it's a bivariate Gaussian distribution. And from this Gaussian distribution, we just draw n samples, so n different temperatures and pressures. For all these different temperatures and pressures, we perform simulations, and we evaluate then that sample using a fitness function. And then we update the multivariate Gaussian in such a way that it moves towards higher values of this fitness function. So the order parameter that is able to distinguish the target phase from the competing phases is based on the diffraction patterns. I already told you that quasicrystals can be identified by their diffraction patterns because it gives Bragg peaks, but then with a rotational symmetry that is forbidden for a crystal phase. And we use a convolutional neural network that can classify these diffraction patterns. So for that, we just perform simulations for the fluid, the square, the hexagonal phase, and the 3 quasicrystals. We save 10,000 independent configurations. We calculate the diffraction patterns, and then because the diffraction patterns are not rotationally invariant, we also rotate it by random angles, such that the network is able to learn to recognize each phase independent of its orientation. And so we use it for our convolutional neural network. We train our convolutional neural network in such a way that it can classify all these diffraction patterns. And then the output layer consists of 6 different nodes that tells us what the probability is that this diffraction pattern is corresponding to one of these different phases. And so because it gives the probability that it belongs to one of these phases, we can use that just as a fitness function for our evolutionary strategy. So if you, for instance, take the output node which belongs to the 12-fold quasicrystal, it gives us the probability that it belongs to that quasicrystal. We can start, for instance, with our evolutionary strategy algorithm in the fluid phase, have this bivariate Gaussian distribution. We take n samples from this bivariate Gaussian distribution, perform simulations there, and then we update it in such a way that it moves towards higher and higher fitness values. And so the fitness is shown here on the right at the bottom. So it goes from a fitness value of 10 to the minus 6, and then it increases over the different configurations towards 1 in about 10 generations. We can also take the other output node, for instance, that corresponds to the hexagonal crystal phase, and then our inverse design method is able to also inverse design the hexagonal crystal phase. We can also see how it transfers to other model systems. We can also look at by changing the shoulder width as the design parameter. And also in this case, we were able to inverse design the 12, the 10, and the 18-fold quasicrystals. Here we also looked at other model systems. So without retraining the neural network, we now applied it to a softened core shoulder potential. And also in this case, we were able to find the dodecanonal quasicrystal without retraining the convolutional neural network. For this system that is much less studied than the square shoulder potential, we also tried to find new quasicrystal phases, and in this case we were also able to discover a completely new quasicrystal phase, which is the 10-fold quasicrystal phase. And then finally we extended it also to a 3-dimensional system, colloidal rods that are coated with, for instance, a microgel, and has a soft shoulder as well. And these systems can also form smectic layers with quasicrystalline order, and also in this case by feeding in just 3-dimensional diffraction patterns, which are difficult to interpret by a human eye. The neural network really doesn't have any problems with increasing the dimension of these diffraction patterns, and was able to also find this quasicrystal in this system. So this brings me to the conclusion. We can use principal component analysis, but also more complicated machine learning methods to find the relevant order parameters and to classify different phases. We can use them in nucleation studies. We can also coarse grained systems by going towards machine learning potentials, and we can also inverse design target phases using convolutional neural network in combination with diffraction patterns. So this work was done by a great team of people: Gabriele Colli, Robin van Damme, Emanuele Boratini, Gerardo Campos Villalobos. Some of them were co-supervised by Laura Villion and René van Rooij, and all the experiments were done by the group of Alfons van Blader, Arnoud Imhoff, Petra Béjot, and executed by Ernest van der Lee and Anna Lenkova. And I would like to thank you for your attention.
Okay, do I have sound? Maybe not quite yet. No? No.
Yeah, I think we can hear you.
Yes? Okay, now it works. Okay, thank you very much, Margaret. Let me first look at questions, the remote questions, and I guess that I have to start from the bottom, Mike, is that right? Okay, you know, that's the earliest question is from somebody who has the screen name Jens, so I just refer to Jens as Jens, and sorry?
Probably Jens Winkelmann.
Okay, yeah, Jens Winkelmann. And Jens says, I might have missed it in the presentation, but how did you generate the labels FCC, BCC, etc. for the training data set with which you trained the neural network? And how large was your training data set? And how large the test data set? So this is a typical machine learning question, of course.
Yes, so we can create these configuration BCC, FCC, HCP, because we know how the unit cell looks like. So we generate these configurations, we equilibrate them in the simulations, and then we use them in the PCA. Does that answer your question? So we use PCA, principal component analysis here, which is actually an unsupervised learning method, but we already use labels BCC, FCC, HCP, because we generate it in that way.
So Jens, the only thing you can do is to type in yes or no. Jens is silent, but let's assume that the answer is yes for the time being, and he can always come back. I will take a second question. Yes, it is yes indeed. Okay, good. It says yes, thank you. The second question is also a remote question. It's from Andrea Liu, and I will do that first so that she can relax before her own talk. And Andrea asked, for inverse design, it would be very interesting to design a process that will yield a structure that does not correspond to the global free energy minimum, but to a local one. Have you thought about how that might be done?
Yeah, at the moment we are combining the inverse design method with also free energy calculations. Somehow it worked very well here because the barriers weren't very high. But if you want to self-assemble phases that are more difficult to nucleate, you really need enhanced sampling techniques. But the benefit of these enhanced sampling techniques is that you also have access to the free energies. So we can now also combine it with free energy calculations, and we can look at metastable states as well. And so the idea next is to also be able to sculpt the free energy landscape in such a way that you can have self-assembly pathways that are easier for experiments as well, and that you don't get into kinetic traps and etc.
Okay, well, I think that's a clear answer. Let me see if there are questions in the audience here at this moment. Not immediately. I mean, I do have some questions myself while the audience is pondering what they would like to ask. And one question actually I would have expected from the audience is when you do the machine learning for the polymer colloid mixture, you compare with simulation, but of course there's also a theory that takes many body interactions into account, at least to some level. That's the scaled particle theory. That's why I was looking at the audience. Have you compared with the theoretical prediction of scale particle theory?
Yeah, because that we actually already did very long time ago. If you take into account the many body interactions, then the phase diagrams are very well in agreement with the free falling theory that takes into account the scale particle expressions.
Okay.
Yeah.
I still look around. Oh, sorry. Yes. Where? Oh, now it's the bottom. Okay, sorry. Michael de Vrucht asked, what if the system's steady state is not obtained from free energy? For example, because the system is active?
That's a very good question. That's actually also on my wish list to do next. So we can use these inverse design methods now for equilibrium systems, but the next cool thing would be to go to steady states and to inverse design steady states or out of equilibrium self-assembly pathways. Yeah.
Okay. I have one question myself. This is about the AB13 phase, where you look at the nucleation from the crystal from the concentrated suspension. But what I remember from the very early experiments of Peter Pusey and Peter Bartlett, Paul Bartlett, is that actually the AB13 crystal often formed from a solution that didn't have at all an AB13 composition. So my question is, what was the composition from which you nucleated the AB13 crystal?
Yeah, we made it easy. We took the stoichiometry of the AB13 crystal phase. If you take another composition, then it should also fractionate, and that makes it more difficult. I think. Okay. I think you can get complex pathways towards the equilibrium system.
Right. I look around. I think I see no additional questions. Sorry, am I missing something? Rafi. Sorry. The boom will come to you.
Thank you. Beautiful talk, Agli. In the first part, you talked about describing or identifying the order parameters as eigenvalues by principal component analysis. Suppose you have a system, let's say, out of equilibrium system. This is somewhat related to the fact that it's not free energy only related. You have a system, you've done many simulations, and then you define a parameter space and you do your principal component analysis, and you find some, I don't know, 1, 2, 3, 4 eigenvectors that are dominant. Can one, from those, defer back what really are what's the basic physics? You see, I'm a theoretical physicist. I would like to know how machine learning would help me get insight into modeling the system theoretically as well. Is there a way to do that?
I think it really depends on the system. I still think if you do machine learning, you have to think yourself as well. So it really depends on what your input is, what features do you put in. If you don't put it in, you never get it out either. So you still have to think when you are doing machine learning. I think in some systems, we also applied the principal component analysis, for instance, for the feedback model. There you also have to feed in, for instance, the velocities or of the particles.
Was that really your question, Rafi? Maybe I can then repeat Rafi's question in my version, but maybe the question is really, if once you've done the analysis and you have a composition, say a combination of different order parameters that contribute differently to what seems to be the important thing that determines whether something happens, does that inform that the pattern that you have detected, Does that tell you something new about the physics? So when you looked at your analysis, did you suddenly find out, well, the really important thing for this event is actually something that we hadn't looked at before?
Yeah, it's really
Was that what you meant?
depends on what you put as input. If you don't put it as an input, you never get it out. So I think it can be useful. For instance, if you go to liquid crystals, or if you go to Landau theories, where you have an order parameter expansion, and you don't know which order parameters are relevant, you can use machine learning to get the relevant order parameters. So for instance, in liquid crystals where you have polarization, but also the bend deformations or other deformations in your nematic director fields, you can get a clue what are the relevant order parameters that you should put in later on in your non-Duchenne theory.
Okay, I think that in view of the time, we'll have to stop here. I should like to thank Marjolein once again for a wonderful talk. And then we go to the next contribution of this afternoon session, again virtual. It's Andrea Liu from Penn, and she will be talking about using machine learning to build a theory of plasticity. Andrea.
Hi. I can't see you guys, but thanks very much, and I really wish I were with you, as I had been planning to be. So yeah, I thought I would talk today about, in honor of Sam Edwards, about a rheology problem, and that has to do with trying to understand what leads to brittle versus ductile failure when you shear disordered solids, when you apply mechanical load to disordered solids. And we've been using machine learning to try to get some idea of this. But machine learning has really been used, I think, in a somewhat unusual way. So that's what I want to tell you about today. You know, when you shear a disordered solid, right, if it's ductile, you see a stress strain curve that looks something like this. Can you see my mouse? Let me actually, sorry, I should have thought of that earlier, change my thing to a spotlight. Okay, how's that? Can you see that better? Okay, so you have the stress strain curve. You know, initially the system responds elastically, but eventually it yields. And if this is the ensemble average over many realizations of doing this, but if you look at any given one, if you do this quasi-statically, so infinitely slowly, and at zero temperature, what you see are these stress drops, right? Individual stress drops. And each stress drop corresponds to not just a single, you know, localized rearrangement, but actually to an avalanche, a series of these rearrangements. And that's really what we'd like to understand. Now, if you have a ductile system, you have that stress strain curve that I showed you earlier. This is just showing them over the same strain range, so the ductile one will flatten out. But the brittle one, you'll see this, it'll show something like this. And this is, you can do this as an ensemble average, and you will actually see large stress drops. Okay, not always at the same place, but you'll see this very large stress drop. And when you see that large stress drop, if you look at the accumulated displacement of the particles in that during this process, okay, this is what it looks like over the strain range in the ductile system, but in the brittle system, you see this very sharp shear band. So So that's a big difference. But if you look at what's happening during the process, okay, it looks very similar. So here's the ductal system. What you see during a stress drop is localized rearrangements that sort of fluctuate around and then hop from one location to a rather distant location. And if you look at the brittle system, you see that it looks the same, right? You see these things that hop around. It's just that all the the rearrangements in the case of the shear banding system are concentrated in this region where the shear band is, okay? So what's happening, the process of having localized rearrangements that can trigger other rearrangements is similar in the two cases, but evolves in the evolution of this is very different in the brittle and the ductile case. So that's what we would like to be able to understand. So there's very nice work from Mathieu Biart's group a few years ago, where they showed that if you take an elastoplasticity model, and you assign each site in this model, lattice site, a yield strain, it's really the low tail of that yield strain distribution that determines whether you see brittle or ductile behavior. So that if you put in a yield strain distribution that looks like this one, this light one, you see ductile behavior. And if you put in one that looks like this dark one, you see a large stress drop and brittle behavior, okay? But we know that actually how ductile or brittle a system is depends on how the system was prepared. So here is exactly the same system. These are simulations from Ludovic Berthier's group, where they have polydispersed systems that they can equilibrate extremely well. And if you quench from a rather high temperature to zero temperature, you end up with systems that respond in this ductile fashion, the black curve. But if you quench to equilibrate to a very low temperature before quenching to zero, okay, you see this large stress drop, you see brittle behavior. So this is the identical system with identical interactions. It's just the only thing that changed was how it was prepared. And so the difference between in this case, the ductile system and the brittle system is purely structural, okay? And so the question is, can we understand this by taking structure into account? Instead of putting in a yield strain distribution by hand, can we capture this transition using structure? So how do we do that? Well, previously in my group, we developed this quantity, which we call softness, not a great name, but I apologize for it. But the idea of softness is it is a weighted average of the local pair correlation function of a particle. Okay, so the softness is associated with each particle. Okay, and if I calculate the local pair correlation and weight it by some weighting, which is the same for every particle, okay, the idea is to use machine learning to infer this weighting function. Okay. In order for the softness variable to have a very strong correlation with whether the particle will rearrange or not, okay? What we found is that particles that are much more likely to rearrange end up having lower first peaks of their pair correlation function and higher valleys, and so that the weights are concentrated at the peaks and valleys of the pair correlation function. All right, so softness really, and this was for glassy liquids, softness ended up giving you a measure of the strength of the cage in which each particle is trapped. The real benefit to introducing this variable softness, the structural variable, is that when you use the same weights, okay, at multiple temperatures, and you look at what is the probability that a particle will rearrange, okay, as a function of temperature, so log of the probability versus 1 over temperature, for particles of different softness, so each color here is a different softness, what you find is that the behavior of this is Arrhenius. Okay? In other words, for particles of given softness, the probability of rearranging has this form, and there is a well-defined energy barrier for each softness for the particle to rearrange. Okay? So that high softness particles look like this, low softness particles look like this. And if you plot the energy barrier, for example, as a function of softness, what you see is that it is lower for particles of high softness than for particles of low softness. Okay? What is the advantage of this? Well, the energy landscape, right, is a 3 n-dimensional landscape. It has, of order e to the order n minima, huge number of minima, and trying to calculate the energy barriers is a very laborious task, right? And so the idea of this is simply by looking at the structure, very simply calculating this local pair correlation function, you can get an idea of the energy barrier that the particle needs to overcome in order to rearrange. Okay, so so this is useful, and it turns out to be true for many different systems. So we originally did this for the Cove-Anderson model. It's a Leonard-Jones mixture. It's what's called a fragile glass former with strongly super-Arrhenius behavior. We can also do it for a model of silica, which is what's called a strong glass former. In other words, the relaxation time is nearly Arrhenius with temperature. And not only that, we can do it for systems. This is the Vertex model of tissues, epithelial tissues, but that shows sub-Arrhenius behavior. Again, the probability of rearranging is Arrhenius for in this case, cells of a given softness. And here we actually applied it to a crystalline system. This is aluminum polycrystals. So with grain boundaries, it turns out that the soft particles are in grain boundaries, right? Particles of very low softness are in crystal regions, as you would expect. And again, even in this system, the probability of rearranging is Arrhenius, so we're getting the energy barriers, and these energy barriers are of the magnitude that you would have been measured for aluminum. So, so softness tells us this energy barrier across the whole spectrum of possible behaviors, from strong to fragile to even sub-Arrhenius, and across the whole range from order to disorder. Okay, so the question is, can we use this, a similar quantity, to look at plasticity at 0 temperature? So we did the same thing. We construct a pair correlation function. Okay, for the weights, I should have said how we trained the system by showing it particles that are rearranging, particles that have not rearranged for a long time, or in this case, a very long strain. And what we see here is the probability of rearranging as a function of softness is an extremely sensitive function of softness here. Okay, varying by over 4 orders of magnitude, okay, over this range of softness. Okay, so this is for 2-dimensional jam packings of Hertzian particles under athermal quasi-static shear. And we see that softness is really an excellent predictor of what is the probability of a particle to rearrange. All right, so now let me take some time for some philosophical remarks, which is, what is the whole point of this? I mean, why would we want to be able to predict a rearrangement, or in this case for plasticity or glassy dynamics, for these energy barriers, right? Well, in this case, right, in the case of plasticity, what we want to understand is what leads to ductile versus brittle behavior. In the case of the glassy dynamics, we're after a different question. What can we want to understand the glassy dynamics? One approach that has been used for glassy dynamics that has gotten a lot of attention is to use machine learning to predict rearrangements in the future. What happens a relaxation time later? Okay, and the analog of this is something that people have paid a lot of attention to as well. In the case of plasticity, can you predict rearrangements at a much later strain of order the yield strain? Okay, so that's not what we're doing at all. Okay, we're using machine learning to predict whether the system is, whether the particle is going to rearrange now, not later, okay? And so why would we want to know that? That's a much easier task. Why would we want to do that? And the reason why we want to do that is because if we're looking at behavior, a yield strain or a relaxation time later, okay, what happens between now and this time in the future is inherently chaotic, right? And so it depends on all kinds of forms of noise, including in our case, numerical noise for the athermal quasi-static shear. And it's been shown that structure actually tells you very little about what happens then, okay? So our idea is to instead use this instantaneous structural predictor, okay, in order to predict statistical properties of the system at this future time. Okay, so we're not trying to project where is the next rearrangement or what's happening exactly in the future. We're trying to just understand statistically what would happen. And so what we are doing is to use this quantity, softness, to look as a tool to characterize structure, to look then at the interplay of softness with dynamics, the rearrangement, with elasticity, okay? So the interplay of rearrangements and elasticity is what has been embedded in elastoplasticity models, okay? Rearrangements give rise to some strain far away, okay, or elsewhere. That strain can trigger another rearrangement if that strain exceeds the yield strain locally, right? And so that interplay of strain and rearrangements gives you avalanches, for example, or gives you the evolution of the system under strain. What we're trying to do is to use softness to develop an enhanced version of this to add structure into this. So a structural elastoplasticity model, and that's quite a mouthful, so we shortened that to a step model, okay? So the idea, what I'm going to show you is that what we've found by analyzing these systems is that we end up with a step model that looks something like this, that there are rearrangements, okay? These rearrangements actually lower the softness nearby. They also raise it far away through the volumetric strain, okay? So that softness determines a yield strain, which when combined with the deviatoric strain that arises from a rearrangement can push the deviatoric strain can push a particle of a high enough softness or a low enough yield strain over the edge to rearrange again, okay? So this is the model that we end up with, and what I want to show you now is how we step through, how we analyze particle simulations, okay, in order to derive this model. So the first piece is to understand this, and this is what has been done before with elastoplasticity models, is say, how do rearrangements give rise to strain elsewhere, okay? And there are sort of two pieces, well, there are several pieces. One is, I can think of, there is a volumetric strain, which has this transient piece that is isotropic and a non-transient piece that is dipolar. So if we look at, it has this form, and here is the, so if I look at the dipolar piece, for example, I look at how it decays with distance. It decays as the expected power law. This is in 2 dimensions. It also has an angular form, which is dipolar, okay? And the transient piece is isotropic, so it survives when I take the angle average, but it is transient. Okay, then there is a deviatoric strain. Okay, this piece is actually not usually included in elastoplasticity models, which decays like 1 over r squared and is isotropic. And this comes from the fact that I can trigger what this, well, hold on, I will say that for later. And then there's what elastoplasticity models usually contain is the shear strain in the direction in which I'm shearing, which is the XY direction, okay? That has the expected quadrupolar form and the 1/r² decay in 2 dimensions. All right, so that's how rearrangements affect strain. Now, the next question for us is how do rearrangements affect softness? So we're going to look at all these different pieces of the interplay, okay, of softness, rearrangements, and strain, and we're going to look at them pair by pair, all right? So the next thing we look at is how do rearrangements affect softness, okay? And it turns out that if I look at how they affect softness, here's the change of softness. You see it has the same dipolar form as the volumetric strain, and in fact the same decay with distance. And if I just look at the angle average, it looks like the transient piece of the volumetric strain, okay? So what in the far field, that's the red curve. Sorry, softness is black. Oh, hold on. The blue is the volumetric strain, okay, and softness is black, and it agrees well. All right, so what that tells us is that in the far field, that rearrangements give rise to a volumetric strain, and that is what is enhancing softness far away. Okay. So, because that is, right, the volumetric strain is giving you a dipolar pattern, which is compressing the particles here, that makes them less soft, and dilating the system there, that makes them more soft, okay? And in fact, so that gives us this piece here of this equation where the change of softness has this piece that's proportional to the volumetric strain, okay? And those are these arrows here. All right, what happens closer? Well, it turns out that the change of softness depends on the softness of the particle. How much its softness changes depends on its own softness. And in fact, it has this form. It looks like this. The change of softness has a piece which depends on how different the softness is from the average softness, from the mean softness, okay? As well as a piece which is just a constant here. And there's also, if we actually look at it, there's a distribution, and so there is a standard deviation. There is some noise on this, so we include that noise as well in this. All right, so a rearrangement then not only gives rise to this volumetric strain that raises the softness far away, but it actually, in this case, lowers the strain nearby, okay, the softness nearby. Sorry, so it makes it less likely to rearrange nearby, more likely to reach further away. All right, what is the next piece? The next piece is what is the effect of strain on rearrangements? So, so what we did for this, we looked at the pair correlation for rearranging particles. If I have a rearranging particle at origin, what is the probability that I have a rearranging particle some distance r away? Okay. And this pair correlation function, okay, if I look at it, is actually isotropic in angle. The angular dependence is isotropic. And what that suggests is that it's the shear strain in any direction, okay, not just the XY direction, that can trigger a rearrangement. And this term then should depend on the shear strain. Okay, if you remind yourself of what we found earlier, it's the deviatoric strain here, which is angularly isotropic. Okay, and that is what we're seeing in the pair correlation function for rearrangements. What about the power law? We're seeing it's not a great power law, but large distances, it seems to be converging something that's sort of like 1/r cubed, not great. Well, the idea is that there is actually a distribution of yield strains which has a tail, a low tail, which is a power law, and the strain scales like 1 over distance squared, so the probability of yielding should go like 1 over r to the minus 3.2, which is, very consistent with what we have. Okay, so so that's that piece. The rearrangement can give rise to deviatoric strain, okay, which can cause more rearrangements. All right, but the yield strain has something to do with it. So what is the yield strain distribution? So we then looked at the yield strain distribution for particles of different softness. So the softness here is given by the color. Very high softness particles are red, low softness particles are blue. And what you see is that this yield strain distribution, because it is an extreme value, it's a minimum, is Weibull distributed, has the form of an extreme value distribution, the Weibull distribution, with a mean which decreases with increasing softness. Okay, so the softer it is, the lower the mean local yield stress, and with also an exponent that depends on softness. Okay, so the low tail gets bigger as you increase the softness. So altogether, this tells you that the soft particles are much more likely to yield, which is something that we knew, right? That we expected should be true, given that we could predict so well the probability of rearranging. Okay, so that's the thing. So that in thermal systems, we found that high softness particles have lower energy barriers. In these athermal systems, we find that high softness particles have lower mean local yield strains. All right, so that sort of completes the model, right? It's the softness that determines the local yield strain, and then the deviatoric strain can push the system over the edge to cause a rearrangement. So now we can incorporate this into a lattice model, right? That's the idea, that we could then try to take this and get away from these particles-based simulations and put it on a lattice and look at it and see if then we can understand what's happening, okay? So, so we put it on a lattice, we allow the rearrangement to change a softness, which is assigned to each lattice site. The softness determines the yield strain distribution, and the rearrangement also gives rise to a deviatoric strain, which combined with the yield strain determines whether we have another rearrangement. So, so this is the particle-based simulations that I showed you earlier, ductile case, and here is what we see in the step model. And you see it looks really quite similar, that you have these localized rearrangements that can appear far away. Okay. It can jump around and appear far away. So qualitatively, it looks very similar. Quantitatively, it's really very good. So here's the stress-strain relation. The black are the particle simulations, and the blue are the results from the step model. And this is the stress-strain relation. This is the distribution of stress drops, so the avalanche size distribution. And here's the distribution of softness, which, of course, as you're shearing it, that distribution evolves, and in steady state, it looks like this. Really very good agreement with the simulations. So, so the step model is really providing a reasonable quantitative description, not only a qualitative description, but a quantitative description. So now I'm going to go on to tell you about very recent work, which is really not totally digested yet. So please forgive me about that, but I'm excited about it, so I wanted to show it to you. So here's the stress strain curve, right, that I showed you before for the ductile or the brittle system. And that's what we want to understand, this difference. Now, we thought, okay, we have our softness, we'll just calculate what it is on the brittle system and then go through the same exercise as before and to find the step model that corresponds to that. But then we ran into an immediate problem, which is that softness turns out to be a very poor predictor of local yield stress in brittle systems. So our strategy was, right, we would train on rearrangements. So we would give the machine learning algorithm particles that we're going to rearrange. We're rearranging on particles that had not rearranged for a very long time, and we're not going to rearrange for a long time. All right? And from that, we obtained the structural quantity softness. And then we found that the softness actually did correlate with the local yield stress. But then that doesn't work in brittle systems, okay? So then we thought, and I have to say we have not worked out all the whys, okay, although I have some ideas. But just in purely practical terms, we thought, okay, well, let's just train directly on the local yield stress, okay? And so we went through the same process before. We set up our, what are the weights of our local pair correlation functions? Let's try to infer them. And it did extremely poorly. We could not train directly on the local yield stress, okay? So out of desperation, and I should say the hero in all of this work is good Zhang, my postdoc, said, okay, I'm just going to use ResNet, okay, and train on images where my particle of interest is at the center of the image, and then I include some small neighborhood around it, and I'm going to see if I can train ResNet, which is good at image classification, to classify the particles which are rearranging the ones that are not, okay? That actually works quite well. And the surprise was that not only did it work well to predict the local yield stress strain, but it actually worked to predict rearrangements better than if we had trained directly on rearrangements. Okay, if we had trained ResNet directly on rearrangements, it does not actually work as well as if we to predict rearrangements as it would if we trained on local yield stress. And why do I say it doesn't work as well? It's because the probability of rearranging is actually a stronger function of, this case, in the black case, it's softness, in the red case, it's the predicted local yield stress. It's actually a stronger function. It rises over the same range over a smaller range of values of softness, okay? So it actually works better. It's more predictive. So what do we get from this? The stress strain relation, here's for the ductile system, here's for the brittle system. These are now the simulations, we're comparing now to simulations from Miyazaki Ozawa from Ludovic Berthier's group. This is not softness, right? Because we're trying to predict local yield strain now. So we call it Y. It's a structural predictor of local yield strain. And this is the behavior of the average value versus strain in the ductile case and in the brittle case. Okay. And what we find is that for the brittle case, there is actually a term proportional to XY strain that now this coefficient becomes important. Okay, before it was negligible, now it's important. So when we do that, right, we do manage to capture ductile versus brittle behavior. That the ductile system, the stress strain curve rises and flattens out, and that we do not see any shear banding. For the brittle system, we see a shear band, and we see this drop in the stress strain relation. Not as big as in the simulation, but we do see it. And we think it's likely, based on what people have done before with elastoplasticity models on work of, excuse me, I'm blank. Oh, yeah, Kirsten Martins, of course. Work of Kirsten Martins shows that you can get much better quantitative agreement stress strain curves if you vary the lattice size. We've just fixed the lattice spacing to be the size of a particle here. We haven't tried to vary it. How am I doing on time? Do I have a few more minutes, or am I close to the end?
2 or 3.
Oh, okay, perfect. I just want to say a word because, of course, our goal here is to have everything in the end, right? We want to not only be able to describe athermal systems under load, but thermal systems under load or thermal systems without a load, okay? Thermal systems without a load, we'd like to be able to look at glassy dynamics. And so the idea is that we can add temperature, right? Using, using an ironing approach, right? So that there's an energy barrier that depends on softness and the local stress and strain, okay? Stress and strain. And I can overcome this energy barrier with temperature, okay? Because we know that the energy barrier in the absence of a strain depends on softness. We know that the softness tells us about the local yield strain. And so we should be able to then incorporate the elastic energy along with this energy barrier and put that in with an ironing form. So that's the idea. But the first step was just to look at systems that are in thermal equilibrium, okay, and look at their dynamics. So no loading at all, no strain on the system, not applying any stress to the system. Okay, so for systems that are in thermal equilibrium, right, and then this interplay, whatever you write down for this interplay, it has to obey detailed balance and time reversal symmetry. Okay. The other thing, and this is what we had before, Sean Rideout has shown, you know, that there are relations between this coefficient here, okay, of how does the softness change? How does the softness change depend on the difference of softness from its mean value? But there has to be, in order to obey detailed balance and time reversal symmetry, you must have a relation between this coefficient and the noise term, right? These are not totally independent things. And so that we incorporated that because, it gives reasonable results for example, the relaxation times and temperature. It turns out that the effects of elasticity are only important at temperatures below the mode coupling temperature. That's work by Rahul Chaco recently. This is also in collaboration with Olivier Dochot, Giulio Biroli, and David Reitman. And so if I'm above the mode coupling temperature, the only I don't need to worry about these long range effects. It's this short range dynamic facilitation that matters. Okay, and that's what we've worked out the form of. So we're making progress on that. You know, it's still at an early stage yet, but you know, we can see we're hoping that we can see our way towards getting there. Oh, okay, I had highlighted this. Sorry. All right. So just to sum up, then, what I've shown you today, right, is that softness, or alternatively, a structural predictor of the local yield stress, okay, are quantities that we can obtain by machine learning, and they're highly correlated with rearrangements. This softness, I can either view it as a particle-based quantity, or I can view it as a field, right? Must interact with rearrangements and elasticity, and that interplay is something that we have figured out how to untangle that interplay for any system you like, okay? If you have the simulations or the experiments, then we now have the prescription for how to untangle that interplay pair by pair and look at how each quantity affects everything else, okay? And that allows us then to construct a step model, okay, structural elasticity models from either particle simulations or experiments. Then I also showed you that, you know, our early attempts at constructing these step models are actually doing reasonably well, and even promising for describing the ductile to brittle transition, you know, without putting things in by hand, like a yield strain distribution by hand. So we're now extending this, we're applying this to experiments on pulled adhesive granular pillars by Hangi Xiao and Doug Durian, simulations of pulled polymer pillars. This is with Entar Yang, Robert Ivancy, and Rob Riggleman. And as I mentioned before, Sean Rideout, my student, is applying this to simulations of the Cove-Anderson model, the non-zero, above the mode coupling transition. So just to show you the people who actually did all the work, and especially my terrific postdoc, Good Zhang, who is no longer my postdoc. Sadly, on September 1st, he started a faculty position at the City University of Hong Kong. And my other collaborators here. So thanks very much for listening.
Thank you very much, Andrea. Let's see what the questions are on the Slido system. Art?
Hi, Don.
Not yet.
Oh,
That's what that means.
so,
Nobody's asked.
oh, nobody's, oh, please, yes, go ahead, but you have to wait for the boom and you have to mention your name.
Yeah, I can't see the room.
It should come up, no? Okay, sorry, yes. Oh, no, sorry, it was the first question was there. That's right. Sorry. Here, just you're just there.
Hi, that was very nice, very interesting presentation. My name's Megan Povey from University of Leeds. I'm just wondering how applicable your work is to real brittle materials. These generally fail through crack and crack propagation. The cracks propagate at the speed of sound, and in very many brittle materials, these fail through crack avalanches. And the crack avalanches are generated by the outgoing acoustic pressure pulse generated by the initial crack. And I'm just curious as to how you think your work relates to that, which is kind of the way I think about these things.
Yeah, so we haven't, that's a great question. That's more ambitious than what we're doing right now. So we're just trying to predict the initial formation of that crack, the shear band that leads to that crack. So we're at a much earlier stage of the process. Okay, so everything I've showed you is up to the formation of that shear band. Now, softness breaks down once there's a crack. And for interesting reasons. It turns out that, for example, we tried to apply softness to thin films, to the glassy dynamics in thin films. And near an interface with vapor or nothing, okay, which is what you have inside a crack, what we find is that softness, there is it's been well known in thin films, okay, that the dynamics speed up near the free surface, okay. Softness utterly fails to predict that. In fact, there's no change of structure of any kind we found with machine learning as you go to the edge of the film until you're very, very close to the edge. And yet there's quite a bit of speed up of the dynamics, even further into the system where there's no change of structure. And it turns out that that's from a piece in the probability of rearranging, which there's a piece that does not depend on structure. And we're in the process of trying to understand that piece.
I'm afraid at some point we actually will have to move to next
sorry.
week. No,
Anyway,
I'm very sorry.
right now we cannot predict what happens once the crack is formed. Short answer.
Thank you very much. In view of the time, we really do have to move to the next speaker. So once again, Andrea. And we are now ready for the last speaker in this session, Jeff Chen, University of Waterloo, who will be speaking about machine learning solver for the modified diffusion equation and application in polymer physics. And hopefully the image will appear soon. I know they have to wait for it to save. There, fantastic.
All right. Okay, well, I wish to thank the organizer for the invitation. I'm sitting a meter away from a screen. I hope my online colleagues are doing the same, so that we can be 2 meters apart. At least the Canadian government recommends us. So we know machine learning is an excellent tool for identification and making prediction. So I'm going to present something that's probably a bit unexpected. Namely, we're going to ask machine learning to solve differential equations. The idea surfaced about 20 years ago, and it has percolated through the field of applied mathematics and computational physics. Of course, real fun starts. The particular version I'm presenting today follows the paper, our own paper, and so it might differ from some other proposals. I'm going to start by reviewing something that we're all very familiar with from 30 years of quantum physics. There is a variational method, variational principle we're so used to use. That is, in order to find the ground state of a quantum mechanical problem, we would design a 12 function with a parameter theta. I'm using theta for a special reason. And then we will calculate the expected energy, which now becomes a function of theta. Then you minimize with respect to theta, and with which you can push the derivative to 0. This way, then you have a ground state, estimated ground state. All right, so let's expand based on this very simple idea. Theta, instead of one parameter, let's imagine that we can use many parameters for theta, W's and B's. R could be multi-dimensional as well. Then you do the same thing. You evaluate E based on Hamiltonian operator. And by the end, you will push gradient of E with respect to theta, the set of parameter, to 0. This way you find a minimum. Okay? Now, of course, all this depends on the shape of the function you define. If you define cleverly, if you're lucky, the 12 function actually approaches the real wave function. All right, so that's a bit of a review of the variational principle. So let's then look at artificial neural network. We have seen this graph a lot. Input, hidden layer, output. Of course, that direction is called width, the other direction is called depth. When we say deep neural network, we refer to several layers, several hidden layers. Okay, now you see all these edges and nodes. What do they mean? Well, it's simply a function call. You're familiar with writing a program and you have a done function call. All it does is taking the value of these nodes, go through this evaluation of this function, and place a final value into that node, the final node. During this process, we introduce W and B. These are parameters. Of course, your variable is X, okay? So these parameters are yet to be determined. These are 12 function parameters. So a basic network form is such that you have input layer where you have these variables. You might have D variables. And the output function will be psi, and you might even have multiple output functions, psi1, psi2. This evaluation of this neural network is basically a function call where you have a set of parameter. I call this set theta for now. All right, so that's the basic structure of neural network. Okay, what about the function form? Well, the function form, the so-called sigmoid function introduced in the previous slide, is usually used. There is a hypothesis which is partially proved that says that the hypothesis is called the universal approximator. Basically says that if your network is large enough, this network can represent any function as you wish. Okay? Now, that theorem needs to be taken with pinch of salt. You see, I've drawn this dashed line here. Usually, when we converge to when we go to the last layer, we might need to change the sigmoid function a bit so that it will accommodate the specific physical problem we are looking at. So that's the neural network representation of a function. We're going to use that to solve a very simple example to start with, a one-dimensional diffusion equation. We are so familiar with this equation. Two variables, time, t, and position, x. All right? It represents the physics of a fluid, particles diffuse through space, x. And here you have an external potential, W. And for a particular initial condition, I'm going to use Q equal to 1. I've placed everything on the left-hand side by leaving the right-hand side 0. I'm doing this for a reason. We will see that in a second. All right? So that's external potential. This is unknown function we need to solve for. And this blue box is simply a differential operator. And that is initial condition. So it represents the diffusion of material, and in a potential well, the material will diffuse to the central part. It will form, a condensed region of material. Very simple. For a quadratic potential, we have exact solution. Beautiful. H here is physicist's Hermite function, so on and so. So this exact solution, textbook solution, will be used to benchmark our numerical result. We're not going to use this solution to train our neural network. It's never used. It's only used for comparison. All right, how are we going to train our neural network? Now, if you are familiar with numerical approach to solve this equation, usually you will need to divide the t variable, the t and x spaces, the t and x space into pieces. Okay? Then you use finite difference to represent these derivatives. And then you use a standard traditional method to approximate this operator. And of course, mathematicians will tell you, you got to do a stability analysis and come with stability analysis will go together with convergence analysis, so on and so forth. Okay, that's what a standard traditional method will do. The machine learning solver we are discussing has a different flavor. So I told you we're going to represent this unknown function called Q in terms of a neural network. All right? That differential operator, I will just simply call it a D. That initial condition, I will call it B. B actually stands for boundary condition, but initial boundary is simply conditions. What we are about to do is to minimize a target function called J. J has two parts, dq squared, bq squared. Wow, it's really this part squared. Okay, alpha and beta are two parameters, prefactors we can use by trial and error. The idea is to push this J to 0. Okay, once we push the J, this target function J to 0, of course the differential equation is satisfied and the initial condition will be satisfied as well. And this pushing is a minimization process with respect to the parameters W and B, the 12 parameters. Of course, that's completely machine learning. We know how to do that in machine learning. Okay. Now you also see these brackets here. They represent sampling in X and T space, in the X and T space. Well, for this talk, we'll be using just simply uniform, simple Monte Carlo sampling. We could design important sampling here as well, but I don't want to talk about it now. Okay. So one interesting property of this whole new way of thinking is that all the derivatives analytically could be analytically carried out. For example, the derivative with respect to parameter, well, if you write down the function, you can just do the derivative. And then this deep descent method could be used to find your next b. Of course, you can incorporate so-called Adam method, so and so, to speed up your minimum finding. As well, with this design of function, you could use, we are able to find analytical derivatives as well. They are simply, derivatives of this sigmoid function. So therefore, no finite difference is involved at all here. All right, everything could be done more or less analytically. Now here is the comparison between exact solution and the machine learning solution we found. So on this graph, on the right-hand side, you will see two things. You will see quite a few things. Solid curve represent analytic solution. Circles represent our machine learning solution. Now, of course, you see here, they overlap on each other for different t's, and here you have x. So they agree with each other quite well after we solve the differential equation. Of course, you're going to ask, how would a machine solve differential equation? Well, during the process of minimizing the target function, the machine approaches exact solution step by step. This step in machine learning is called epoch. So starting with epoch 0, the machine still doesn't know the solution. So therefore, these circles, as you can see, are all very far away from exact solution. Now, during the process, you're going to see a movie, and you will notice this epoch number change. That is, we're going through minimization steps. During minimization, you will see how these circles approach the exact solution step by step. So here goes the movie. As we minimize J, the machine learning algorithm finds its solution, and we see agreement by the end. Okay, that's how, that's the principle behind machine learning. So, solver for differential equation. Now, the process and the example I gave you was quite simple, actually two-dimensional, x and t. So let's look at a more complicated problem. What about d dimension? I'm going to make this operator Laplacian d dimension, all right? D will be pushed to a high number, so we'll be looking at a high dimensionality. Can we still use machine learning to solve for this? Now, if you look at the traditional approach, it requires a computational resource that's proportional to some number to the power of d plus 1. This is some number we're talking about is basically a division of your space. Okay, that is an exponential requirement. For example, if I look at 10 dimensions, you already look at the storage space of this number, which of course is beyond the current capacity of any supercomputer you have already. Let's look at machine learning. Machine learning requires no such storage. Well, you might have 10-dimensional input. You still have one-dimensional output if you're dealing with only one function. You have a bunch of hidden, you have two hidden layers with a bunch of hidden nodes, and you have a number of W's and B's. I can push J to 0, with a pre-specified error criteria, I could also estimate the number of epochs the machine goes through to find a solution. Okay, so we will use that example to study how computational time scale as a function of dimensionality, and this is a result we got from on a log-log plot. Now we're soft matter theorists. When we see a log-log plot of this shape, we know immediately we can feed a power law to it. So if you feed a power law to it, this blue line represents d squared, basically. We have gone a dimensionality as high as 64. All right. I don't have the time to go through this, but we could analyze the basic structure of neural network and explain the reason why it is a d squared behavior, power law behavior. In comparison, the traditional solver will require k to the power of d, which is an exponential law. Here we have power law, of course. Power law, exponential law, they have completely different behavior. For D60, our actual calculation spent 12 days, it's 2 weeks. And if you estimate the CPU required to solve such a big problem, traditional method will require 10 to 72 years, plus minus, making the problem almost impossible. So machine learning could be used, this particular algorithm could be used to break curse of dimensionality. In other words, we are now able to solve high dimensional problem. I have more examples of this. But today, I will shift now my attention to a real application, namely solving the self-consistent field theory for AB diblockal polymers. The physics behind it, well, most of us are already familiar with the physics behind it. Basically, you have a diblockal polymer, A and a B, that are tied together in the middle, all right? A and B dislike each other, but they are tied together by marriage. Whether or not you like each other, no, well, good luck. You have to be together, or you can stay away from each other as far as possible. So A will form its own domain, B will form its own domain. In this particular structure I'm showing you, we're talking about so-called lamella phase, and that's usually obtained when the fraction of the volume fraction of AF is about 1/2, 50%. As a matter of fact, as F changes, we are talking about other possible periodic systems that can form. Okay, so this is well developed. There is well developed understanding of physics behind this, and they usually go with 2 parameters, Kn and F. All right, Kn and F will determine your phase diagram, basically. All right, let's see how we do this theoretically. For this, I'm going to introduce a propagator, Q. It represents the probability to find a polymer piece of length T with the leading monomer located at spatial position X. So it's a function of X and T. T represents the length of this polymer. Now this propagator, of course, you can always step back even 1 step by dealing with Green's function. This propagator satisfies a modified diffusion equation, and that's the main contribution of Sam Edwards to formulate, of course, Gaussian chain theory in terms of field theory. And if you look at the structure of Q and the equation we need to find Q, it's identical to the diffusion equation we just solved 10 minutes ago. All right? I've used a length scale such that the root mean square end-to-end distance is used to scale X. Okay, so that's identically the equation we need to solve for a polymer in external field. As a matter of fact, we need to deal with two propagators. One for T, one is complementary segment. We need to deal with L minus T, all right? So we need to solve two equations instead of one, all under external field. Now, if you go and begin to formulate a self-consistent field theory to deal with multi-chain problem, then the equation becomes much longer. The main idea, people might use mathematics to explain this, but I wish to use picture to explain this. The basic idea is that for a multiple chain problem, other chains, you will select a representative chain, other chains will form a field called a W, self-consistent field or mean field. Your polymer, your single polymer will live in this field W. So based on the density, proposed density of your multi-chain problem, you can develop what this W is. You can develop a formula for this W. And then you go ahead and solve your Green's function or propagator. And it is this step we need to use numerical approach. Once you have a Q, you can go back and calculate rho. And once you have rho, you can go back and self-consistently solve for W and so on and so forth. So that's a loop process, a looping process from a traditional method. Now let's see what kind of equation we need to solve. Now I know this page is kind of busy. We have two modified diffusion equations. We have two initial conditions. We have boundary conditions, actually 6 of them. Two Dirichlet boundary condition and two Norman, one set of Dirichlet and one set of Norman boundary conditions. So in total we have 6, all in 3 directions. Then we need to calculate the single chain partition function, Q. And based on that, we can figure out the volume fraction. So now we have to perform integral. And then you need to go back and figure out this mean field. And of course, there is a requirement in polymer theory where your system is incompressible. So you need to actually implement a Lagrange multiplier for this condition. Putting all these conditions together, it forms an integral differential equation, a set of integral differential equations we need to solve. So how are we going to do that? We will represent Q1, Q2, these two propagators by this simple architecture. X1 and Z as input, T as input, go through a hidden layer, we calculate the functions with unknown parameters. These parameters will be determined in just a moment. We will also propose to represent the external mean field. This time they depend on X, Y, Z only. By a neural network, I'm drawing this from right to left. So arrows are all pointing to the left. You know X, Y, Z, you calculate WA, WB. We'll couple them together through the so-called target function. That's our next step. There we go. Here's our target function, J. Now, J has different components. The first, most important one is deal with those differential equations. Differential equation number 1 squared, differential equation number 2 squared. J initial condition deals with the initial condition we need to incorporate. J boundary condition deals with the 6 boundary conditions we need to incorporate. I wrote 2 here to represent it. And then you have these constraints, Lagrange multipliers and so on and so forth. They are all placed here as JC. Now, as a matter of fact, there's one more physical condition we need to deal with, which is minimization with respect to the periodicity of a unit cell. I don't want to get into that detail here. So what I try to explain here is that whatever the condition is, you just begin to add it into this list of J's, the list of cost function. Once you've done that, now you need a good graduate student to carry out all these analytic derivative and then program it. And then you can use a machine learning method to drive J to 0. Okay? Once you do that, you have a solution. Approach is slightly different from the traditional approach. We will treat both Q and external field W simultaneously. I've already shown you the diagram of how to couple them together. Traditional method would deal with W, well, assume a W first, solve for Q, go back, propose your W, and then solve for Q, go for that loop. We try to do this all at once. Now here is our result. We are able to use, that's quite easy to find. We are able to use this new solver to solve for more complicated cases, such as bounded and also gyroid. And the green color here presents a rich domain. All right, so it's a good time to summarize my talk. So we have used the machine learning simple problems, diffusion equations, and more complicated problem, which is self-consistent field theory. Okay? The basic idea is that you define a universal solver without discussion such as Euler method or Planck-Nicolson method or convergence criterion. You don't discuss that. You just put everything into machine learning cost function J. Now I must admit to you, my original thought was using free energy as a target function to minimize. It's quite natural to think about free energy as a functional that needs to be minimized. But my graduate student who did all this work strongly recommend to place things this way, to design things this way, so that we are in a modularized form. All right? Speed and efficiency, well, the solver we developed, I must say, for a three-dimensional problem, it is slower than some of the best traditional method. However, our alternative way of thinking allows us to deal with higher dimensionality. Now, to solve a polymer problem with, say, solve a worm-like polymer problem with a different measure, statistical measure, for example, you might need to deal with a higher dimensionality. And for that type of problem, our method could be more efficient. Machine learning. What is machine learning doing here? Well, we didn't tell machine learning to learn the exact solution. What we tell machine learning to do is one thing, to push the target function to 0. Once it learns this, it can solve almost any other questions we might have. Now that's a scary thought. It will, once machine learns this, it can solve many other problems. It could put you and me out of business. Of course, the writers in Hollywood have known this quite a long time. You see all these scary predictions from Hollywood. Anyway, I want to thank my PhD student who is now actually working for the bank industry using machine learning, solving partial differential equations to predict financial market. And here is my funding agency. I want to thank you for your patience. I need to go back to my meeting portal in order to.
Anyway, thank you very much for a wonderful talk. Let's see, the Slido is empty.
I need to go back to the portal. Somehow I don't have a close.
You don't need to do anything. You're fine, apparently.
Okay, Good. I can hear you clearly.
Okay, good. Let's look around if there are already questions in the audience. Yes, here. And then after Tom?
It might be the same question.
Okay, well, why don't you start?
Let's take back to Tom. I was trying to work out good problems that might be solvable using this. Have you thought about doing first passage problems in polymer dynamics, like Rouse polymers? First passage time?
No, no, I haven't really worked on that particular problem. What you mean is basically solving a problem with multivariables representing the position polymer beads, right? And then, is this what you are talking about?
Yes.
Design and probability function.
Yes.
Okay.
That's a very interesting direction. I haven't really gone that far yet.
I think we have one question on Slido now from Zoe Wang, who asks, she says, Jeff, great talk. One quick question. How do you justify the physical correctness obtained by your machine learning methods?
Okay. Well, how do I justify the physical correctness? For that, this new method doesn't differ from any other traditional methods. You find a structure, you calculate the free energy, and then compare free energy, see whether or not your free energy actually corresponds to the global minimum. Of course, you can't get a global minimum. You can only comparatively compare a few free energies and find the lowest free energy. So the physical justification is that once it has the lowest free energy, I would then say that it's a stable structure.
Okay, there's another question on the Slido. It is by Michael de Vrucht, who asked a question in the previous session too. It is the fact that the computation time scales only quadratically with dimension is very exciting. Oh, it's very exciting. Can this be used, or has it been used, to obtain numerical solutions for the many particle Schrödinger equation where the exponential scaling is an important challenge?
Thank you, Michael, for asking. As if you know me. We just actually published a new paper this year. We solved multi-energy levels for static Schrödinger equation of multi-dimensions. So we have gone as many as dimensionality D as many as 64, energy levels as many as 128. So we can do a big problem like that, finding 128 energy levels. And it is a 64 particle problem. Now, the 64 dimensional problem divided by 3, if you wish. Michael, have I answered your question?
I should first look at the screen to see what Michael says. If not, I mean, could I ask just one short follow-up question to this one? Is, did you compare with existing quantum chemical methods to see whether actually in this particular case you outperform them also? I mean, it's a matter also of computing time. Or is, I mean, I understand this is early days, but, Michael says, yes, thank you. Okay, sir.
Okay. Do we outperform existing traditional methods? As I said, low dimensionality, low D.
No, but I mean, for this high-dimensional, semi-high-dimensional quantum
high
problem.
D, there's no traditional method that's capable of solving D as high as 64 dimension. It just don't exist.
Well, there's the quantum.
Okay, all we can do is push for, say, D8, 8 dimensions, and then compare to our result, the time it takes to solve a problem according to our algorithm. That's what we can do. And we found, of course, our scaling is square and their scaling is exponential.
Tom.
So I will ask my question now because it's a kind of follow-on from this, and it's the question that someone has to ask in every machine learning presentation, which is about how it does it. I know that's kind of not allowed because these things are by definition black boxes, but it is very interesting that something has worked out how to reduce an exponentially sized problem into a power law sized problem. And actually, of course, nature has ways of doing this too. There are many famous exponentially sized problems in nature, exploring a partition function is one, protein folding is another, protein evolution through a vast exponential space is yet another. So there are all sorts of exponential problems that nature managed to turn into a power law. Can you give us some insight into how your machine learning algorithm, do you have any idea so what way does it do it? Does it reduce, for example, the exponential space into a sort of submanifold of finite dimensions that are sufficient for coverage in a sort of ergodic way? That would be the sort of level of response that would satisfy me, though I'm sure that's not the right answer.
Well, you have already explained, you give yourself an answer already. By writing down the sigmoid function relationship and so on and so on, by designing neural network, we have basically cut ourselves into a subspace or a subdomain of the high dimensional space already. Now, it looks to us that machine learning is able to quickly find this subspace. And then following that, of course, it deals with this much smaller space. Therefore, it disregard all this high D, irrelevant space, irrelevant D-dimensional space. The Schrödinger equation we solve in D dimension incorporates the idea of weighted Monte Carlo. Of course, as we know, weighted Monte Carlo led us to focus in the region where things are happening. Okay, so yes, incorporating weighted Monte Carlo will further allow us to identify the region where interesting things is happening, and that is perhaps the reason why machine learning is able to shortcut this. I might wish to add that we are dealing with a neural network with finite number of nodes. The highest we went was 500 nodes. Of course, a higher dimensional problem will require a more complicated design of your neural network. So I lie a bit about this exponential growth and power law growth, because for a higher dimensional problem, for a more complicated problem, you need a more complicated network. So your overhead, this pre-coefficient, overhead needed to compute could become much larger.
Okay, so the lunch is not totally free. I think that there are no questions from the audience nor from the screen, so I think we're at the end of the session, and there'll be some general announcements. Oh, sorry, but first I should like to thank the speakers again. So all speakers, so first of all Jeff, but all other speakers for this wonderful afternoon session.